Asia YouTube channel. Dear friends, we are going to explain the nomenclature of karo. Today we are going to explain the nomenclature of karo and the relation between radius and degree of karo, and this way with a smart concept. First, nomenclature of karo means choosing up name for karo. It means that a curve can be called into by two names, just like a radius of curve and degree of curve. Number first, radius of curve. The magnitude of a curve is expressed according to radius. It can be known as a radius of curve. For example, 100-meter radius curve, 30 feet radius curve, or we can also say that a curve of 400 feet radius, etc. This method is mostly used in highway department. So as you can see that here we have draw a curve. So suppose this is a curve, and its radius. So you can see that here a radius is expressed, which is 400 feet. Now this curve can be called 400 feet radius curve, as we have written here that this curve is called 400 feet radius curve. The second is a degree of the curve. In this method, a curve is expressed in degree of curve, which means that if the magnitude of the curve is expressed according to degree, then that curve will be called degree of the curve. This method is mostly used in US and also used in a railway to provide curve to a railway track. Degree of curve is expressed in two ways, which means that degree of the curve can be expressed in two ways. Number first, length of curve method, number second, length of chord method. So if we measure this curve length and we get a degree, then it will be called length of chord method. So if we measure this chord length and we get a degree, then it will be called length of chord method. So you know that as we know that a curve degree can be get from a curve degree is equal to, which is length of chain divided by radius. So this length of chain can be length of curve, and this length of chain is also can be a chord. So if the length of a curve is taken, then that method will be called length of curve method. And the other, if the chord of this curve is taken into consideration, then that method will be called length of chord method. Now we are going to explain the relation between a radius of curve and degree of curve. As we got that a curve can be called radius of curve or degree of curve, but now we are going to discuss the relation between the degree of curve and the radius of curve. To go find this proof, so consider a curve and its elements to determine the relation between radius and degree of curve. We have considered this curve. So we can see that this is a curve, and these are the elements of this curve, just as mn, which is the chord length, and r, which is the radius of this curve, and this is the curve length, as we have written here that curve length. But discuss these elements. Let's r is equal to the radius of curve in meter, but keep in mind that the calculation is going in metric form. So as we know that d is equal to the degree of curve, and mn is equal to the chord length, which can be 30 meter or 100 feet, but here in this calculation chord length is equal to 30 meter. It means that mn is equal to chord length, which is from this point to this point. This is called chord length and denoted by mn. This chord length can be 100 feet, and in engineering chain are FES and 30 meter and metric chain. But in this calculation we are going to explain in metric chain. It's mean that from the distance mn, which is a chord length, it can be equal to 30 meter. So the other point P, so we can see here this is the P, the midpoint of the chord length. Now by dividing a chord and the midpoint mn at point P, so we can see here that it's mean divide the chord length at the midpoint, which is this is the midpoint and this point is denoted by P. So this distance will be equal to the half distance of the total distance, which means that this is equal to 1 by 2 multiplied by total chord length. So you can see here further we say that so we can get a right angle triangle which is given below. If we divide it's mean that if we divide this chord length at the point P, we get a right angle triangle. So you can see here that this is a right angle triangle that is taken from this and which is given below. So you can see here that this is denoted by O, which is the origin of the curve, and this is the point P, which is the half length of the chord length, and this is the M, which is the starting of chord length. So and as we have taken a right angle triangle and this triangle OMP, as we have considered that the thin line which is the whole curve, but the dark line which shows the considered right angle triangle. And triangle OMP, OM is equal to radius, as we have written here that OM, which is denoted by R, and this R is known as radius of the curve. And the second is MP. So MP, as we have said that MP is equal to the half length of the MN, as we have written here that MP is equal to 1 by 2 MN, which is equal to 30 by 2 is equal to 15 meter. As we taken that chord length will be equal to 30 meter, and we say that MP is equal to the half of chord length. The half of 30 is equal to 15 meter. The other is angle MOP, which is show here that this angle MOP. So this angle is equal to D by 2, as we know that the whole degree of this curve is denoted by D, but this half degree is equal to the half of total degree, which is given D by 2. As we get a right angle triangle, so OMP and radius and its degree, then according to trigonometry, sine D by 2, sine D by 2 is equal to MP divided by OM, which is equal to MP is equal to 15 meter and OM is equal to radius, as we have written here. So it is equal to 15 divided by R. So sine D by 2 is equal to 15 by R. This is equation first. So we can say that from equation first, R is equal to 15 divided by sine D by 2. This is the exact relation. If we find the for higher degree curve, just like higher than 5 degree curve, then we use this exact relation. But up to 5 degree curve, a sample relation can be used. Now simply we can say that where D is so small, sine D by 2 may be assumed approximately equal to D by 2 and radian. As we know that the above relation is in radian form, then convert it into degree, then multiplied by 180 by 5, which is therefore we have written here that R is equal to 15 divided by D by 2 multiplied by 180 divided by pi. So 2 multiplied by 180 is equal to 360. So we can see here that we have written here 15 multiplied by 360 divided by pi d, which is equal to 1718.9 divided by d. So this is the sample relation which is used for direct calculation, but for higher degree curve we use this exact relation which is equal to r is equal to 15 divided by sine d by 2. And simply we can also write the simple calculation just like in two steps. L is equal to r theta. To find degree, divide both side by r, so we can write here d is equal to L by r, which is in a radian form. Convert it into degree as we required into degree, mostly used in degree. Then L by r multiplied by 180 divided by pi, as we have written in previous steps, which is in degree form. So we can get a degree in degree form, because this is in radian and we require to get it into degree. Therefore we multiply it by 180 divided by pi. If we require to find r, then multiply it by both side by degree, we will get a radius. So radius is equal to length divided by theta, and this is also is in a radian. R is equal to L by d multiplied by 180 divided by pi. As we have written here that r is equal to 1718.9 divided by d. This is the simple calculation as we have find in the previous step. So this is a simple calculation, and at the previous this was the exact relation which is used for higher curve. I mean that a curve having more than 5 degree, then we use this relation. But in simply calculation we use this a simple relation. Radius is equal to 1718.9 divided by degree. It's mean that as we have written here that this relation is good up to pi degree curve. For higher degree curve, the exact relation, which is equation 1, is used. So this is the as I told you that r is equal to 15 divided by sine d by 2. Thank you for timing. I